once Roy gets out of the way.
And Kevin will be introducing to us several hot topics or open problems related to the classification and characterization of atmospheres of extrasolar planets. So this is currently one of the most rapidly expanding field in astrophysics. So we are very excited to have him here from Switzerland to this Colloquium. Let me introduce the speaker very quickly. He's from Singapore and did his PhD in Boulder, Colorado. He then went to the Institute for Advanced Studies in Princeton, and from that he went to Europe to take a postdoc position after the Princeton postdoc position as Tricky Prize Fellow at the ETH in Zurich. He liked it so much that he stayed in Switzerland, and since 2015 he's professor at the University of Bern. So the answer to Basel was a typo earlier today. And he's there now the director of the Center for Space and
Yeah, I have the same problem.
He also has a joint position at Johns Hopkins University in Baltimore. So, not much more about the speaker. Let's welcome Kevin.
Thank you for this very warm welcome, and can you hear me? It's fine. Thank you for this very warm welcome and very gracious introduction. In fact, I stumbled on the same word, and when I gave the job talk at Bern in 2012, I distinctly remember I was the only person on the short list of 8 who was a habitability skeptic. I say we were not ready to think about habitability. It's a buzzword for getting money, and my views remain the same. So I guess as you progress in your career, you start thinking about problems in hierarchy. So there are problems I think about myself. There are problems I think about with my group of 4 PhD students and 4 postdocs. There are problems I think about with my center, which encompasses a few independent fellows of 20 to 30 people. And I would like to talk about a cross-section of about a third of the problems I actively think about. So here are 5 problems. So first, item number 0, I would like to sweep you through a review of the observations to convince you that this is not just a theoretician's fantasy. And then I would like to walk you through all of these problems. The problems are designed such that I'm really confident about 1. I'm still confident about 2, and then the confidence goes down in this direction. So these are things I've worked on that I'm very sure about, things that I'm currently thinking about, and things that I'm thinking about but haven't done any calculations yet. So let's see how we get. So let's review the observations. This is a theoretician's review of the observations, and I like to think about it in the following manner. So think of an arrow where on the which signifies the spectral resolution, and there's a spectral resolution of 1, which is basically photometry, and all the way to 100,000. So following the first exoplanet discovery around a sun-like star in 1995, and the measurement of a transit a few years later, in 2007, this was the state of affairs, right? So when you look at this, you almost want to laugh, because you have a very complicated models. Am I holding it the wrong direction? There we go. That's wonderful. So here's an emission spectrum, and this was the state of affairs in 2007. So you have really complicated models. It's fine. Let's not worry about this. So you have really complicated models, and you have just a few photometric points.
So mechanics always works.
Yeah, let's do that. So you have you have really complicated looking models, and you have a few photometric points. And these photometric points, in terms of the physics, resolve the relative strength of molecular bandheads. Nothing close to resolving spectral lines at all. They give you an idea about the relative strength of bandheads, and they don't even resolve the bandheads. And at that point, the debate was on whether atmospheres have temperature inversions and so on. I'm not going to talk about that. That takes like half a talk to explain why it's interesting. But this was the state of affairs. Then fast forward 8 years in the future, in 2015, this is done using the WIF-C3 on the Hubble. And this was done by Jacob Bean and his students and collaborators at Chicago. And now things start to look a little more convincing, such that if you take away the models, you can be almost convinced that you're detecting something interesting. So this is the transit depth as a function of wavelength. This was designed to be centered on the water bandhead. So it's quite convincing, if you believe the error bars, that this planet, in this case the hot Jupiter Warps 12b, seems to have high temperature gaseous water in the atmosphere. So this technique is called spectral photometry because it's not quite spectra. And it partially resolves the shape of molecular bandheads if you know what you're looking at. Of course, there are issues and degeneracies and all that, but that's the idea. Now, if you go one more order of magnitude in resolution, this is the iconic HR8799 system with 4 directly imaged exoplanets. The planets are bright enough, and astronomers are clever enough that they start to begin to take spectra of these objects. So here are the spectra in the black. So the JHK spectra with a resolution of around 100 and a few photometric points. And what you can do with this is, I say almost impressed because this was my student's first paper and it took him a long time to write it and an equally long time to respond to the referee's report. But nevertheless, so these are the 4 data sets. And then we run a technique called atmospheric inversion. So in the traditional modeling sense, you make a set of assumptions, you calculate forward, and you compare chi-square. This method is obsolete in exoplanet atmospheres. The method that we use, which is inherited from the earth sciences and the climate sciences, is to use an inversion method where you go from the spectra directly to retrieve what the temperatures and chemistry are. And the key behind that method is to calculate the full posterior distributions in the Bayesian sense between all of the different parameters. So I'm not going to talk about that, but I'm going to show you the result. So if you believe this technique and you do the inversion, you can back out things like the elemental abundances of oxygen, the metallicity, in other words. And one of the interesting things is that these 4 planets, from the outermost B to the innermost E, seem to have different posterior distributions. This suggests that it is more naturally consistent with a core accretion formation history. And if you want to still interpret the formation in terms of a gravitational instability scenario, you have to work a little bit harder. It's not excluded. But with a resolution of 100, you can start to pose questions like this. You can start to connect atmospheres with chemistry, with planet formation, and start to ask these questions. And as we go forward in the future, we will keep asking these questions. Now, at a resolution of 1,000, which doesn't exist yet, at least for transit photometry in the infrared from space, we are looking forward to JWST. And this is a simulation from 2012 of some configuration. It's not so important. But what is important is that if you observe at a resolution of 1,000 and you bin it down a little bit, you can resolve the different bandheads from the same molecule, and you can also resolve bandheads of different molecules. And that gives you a handle on the degeneracies and the temperatures and the pressures involved. What is less appreciated is that higher resolutions already exist. For selected objects, you can only do these techniques for objects that are very near and very bright. One very niche technique is ultraviolet transit spectroscopy, which is a resolution of about 10,000. So this takes some explaining. This black and blue profile, never mind what the differences are, this black and blue profile is the light from the system with the planet and the star out of transit. Now what's puzzling is that as the planet goes in front of the star and there's a transit, there's a dip in the light, which is not so surprising, but what is surprising is that the dip occurs at velocities up to 100 kilometers a second. Now, if you just do the order of magnitude, this is surprising, because if you do the order of magnitude, the escape velocity from the planet is about 10 kilometers a second. So you're missing one order of magnitude. And there were many explanations put forward to explain the observations. The most natural and promising one, in my opinion, is that you have protons from the stellar wind. The escape velocity from the star is on the order of 100 kilometers a second, the right velocity. The protons from the stellar wind stream out and encounter the escaping hydrogen atoms from the planet. It does a charge exchange. The cross-section is exactly right in this velocity regime. The charge exchange completely dominates ionization and excitation. And you get a population of atoms that trace the properties of the stellar wind. And this is what makes it so challenging to interpret, because this interpretation assumes that you understand what the stellar wind is doing. So you can't exactly back out very exact numbers out of this analysis, but you can answer the binary question, which is there hydrogen escaping from the planet? And it turns out that this binary question is really important if you want to answer questions about whether oxygen or ozone is a false positive for biosignature. And that is, again, the subject of another talk. I can talk to you after the talk if you want, but there's no time to go into that. Now, at 100,000 resolution, this is done from the ground using ground-based spectrograph, like the HARP spectrograph. And you can only do this for very bright objects so that you have enough light to do the splitting at the order of 100,000. So what is surprising about this, and I was not involved in this study, these are my colleagues in Geneva. And what is interesting is that, look, these are the sodium lines. And you would think that blue's the ground and black's HST. It turns out it's the other way around. So the blue line is HST, and we do much better from the ground in terms of detecting the sodium lines. So in Geneva, there's an ongoing campaign using the HARP spectrograph to detect the sodium line in about 60 hot Jupiters. This is ongoing, and we are putting out the papers now. And this method was pioneered by Ignace Snellen in Leiden. There's a very interesting literature on how you can use this method to measure wind speeds, to measure rotation of the planet, and so on and so forth. I encourage you to read this literature if you are curious. So that's my theoretician's review of the state of the art, which took about 12 minutes. That's what I intended. So now let's talk about the 5 problems. So let's talk about transmission spectra. And to talk about transmission spectra, you have to start talking about something called the transit optical depth. It's quite easy to understand. Give me a moment. So this is the telescope, you standing at the telescope. And if you look at the planet, at some point you see an edge at a certain wavelength. This is a wavelength-dependent statement. And this edge is defined by this chord, which has an optical depth on order of 1. That's radiative transfer 101. Right? So now you can do simple geometry. Actually, you can first ask the question, what's the optical depth? The optical depth of the chord is the number density multiplied by the cross-section multiplied by some length. And the question is, what's the length? You know from order of magnitude that the system has 2 length scales. The first length scale is the pressure scale height of the atmosphere, kT over mg. The second length scale is the radius of the planet. You also know that the h is much less than r. So the correct mean between the 2 quantities is not h plus r over 2. It's square root of hr. So when you have 2 quantities that are very different from each other, the correct mean is not the arithmetic mean, it's the geometric mean. Let me give you another example. The Einstein radius for gravitational lensing is the geometric mean between the Schwarzschild radius for the black hole and the distance to the lens. And if you do that, you get it correct to within a factor of 2. So you get the physics correct, you get the accuracy of the physics, but not the precision. And that's what I tell my students a lot. I said, you should not be misled by precision. You should go for accuracy first. And now, if you do the problem properly, you get an extra square root 2 pi. So close enough, right? In fact, if you multiply it by a factor of half, you get pi over 4, which is about 1. So in fact, you get the answer almost exactly correct. Another way of understanding this result is that if you were standing here and not here, and you were looking straight at the center of the planet, the path length would be 10% that of this path length. So you're scanning a path length that's 10 times larger than if you were looking in the center of the planet. There's a point to showing you this. The point is that if you take away all that complication and you put it in a triangle, and I'm sure you can solve this, and you solve for z, you end up that z is pi h over 4. Why is that interesting? Because in atmospheres are to 0th order in hydrostatic equilibrium. That means pressure balances gravity. It means that for every order of magnitude in pressure that you go up or down, you go up or down by 2.3 pressure scale heights. Now, 1 pressure scale height means that you're not even 1 order of magnitude in pressure. So the conclusion is that it's not obvious, but the conclusion is that when you probe a transit, the transit chord is nearly isobaric. So I've given you this hand-wavy argument, but how accurate is this argument? So here's the same with C3 coverage of the water band. In purple is a numerical calculation, an exact numerical calculation. And in blue, red, and yellow are different isothermal analytical calculations at a fixed pressure. So the first thing you notice is that the error is really small. It's small enough that it's an order of magnitude below the noise floor of HST and probably an order of magnitude below the noise floor of JWST. So for all intents and purposes, the result is exact. The second thing you notice that is important to this story I'm telling is that notice that all of the 3 solutions that span 3 orders of magnitude in pressure are nearly identical. And this is not surprising because when you're probing a transit chord that's so high up in the atmosphere, effects such as pressure broadening are unimportant. So the physical intuition tells me that pressure effects, you're not sensitive to pressure effects. And if you are sensitive to something, an effect that's very, very small that you don't fully understand. So I would be worried if you were leaning on pressure broadening to get an answer. So the takeaway message is that you're not sensitive to pressure, and this leads into the story I will keep telling later. Now, I've shown you this formula. Let's look at what the formula is. This is the formula that's validated in the previous slide. So this is the transit radius as a function of wavelength. This is some reference pressure. This is a constant of integration. When you do the integration, you need to integrate from some reference radius that has a reference pressure. This is the pressure scale height. This is something called the Euler-Mascheroni constant. It's just a number. And this is a bunch of stuff in a log bracket. And the first thing you notice is this formula is really useful because it allows you to understand degeneracies without plotting a single diagram. So the first thing you notice is that these 3 quantities are all degenerate, right? So if I increase the opacity by the factor of 10, and I increase the gravity by a factor of 10, it's the same as not increasing anything at all. That's obvious. And this is the pressure scale height, this is the reference pressure, and so on. What is more troubling, let me bring your attention to this, that has been swept under the rug by all of the practitioners in the field, is this reference radius and the reference pressure. So why is this troubling? Because, first of all, you don't know what the relationship is. Knowing the relationship is physically equivalent to knowing what the structure of the planet is. So it's the same as me telling you, tell me the pressure of the planet at 1 Jupiter radius. And if you're honest, the answer is, I don't know, right? Or there could be many, many solutions consistent with the answer. I don't know what the answer is. The second thing that's troubling is that this is hidden in the log, whereas this is outside. This means that a tiny change in this, a few percent or even sub-percent, is going to create an order of magnitude change in this. And if this changes by an order of magnitude, the mixing ratio, the abundance of water or whatever you want to measure, is going to change by an order of magnitude. So this is a degeneracy that was previously noticed numerically, first in 2012 by Banneker and Seeger, and then in 2014 by Caitlin Griffith, but they noticed it numerically, and they did not realize that the degeneracy is not between two quantities, but between three quantities. So the real degeneracy is between R0, P0, and the opacity. So let me show you why this is important. So let me apply it to this resolution 10 spectrophotometry of warps 12b I showed you earlier in the talk. So I take the validated analytical formula. Remember, the formula is validated, so you can't come to me and say your formula is not accurate enough, because I have shown that it's accurate. So now I fit the formula to the data, and I make the same assumption as these guys make. So I assume that the reference radius is this much, and I make an assumption that is this pressure. And I get exactly the same answer they get. I get consistency. What happens if but there are a few flaws in this argument. The first flaw is that, where does this number come from? This number, it turns out, is the so-called white light radius. It's the radius of the planet when you stare at the planet in a wide optical waveband and you measure what the size is. But the white light radius, even if you accept that you can use the white light radius as the reference, and even if you can accept that you can assign 10 bars to it, which is not correct, comes with an error. So now if I vary the reference radius well within the error, what happens to the water abundance? So by varying it from 1.79 to 1.87, which is 0.08, still less than this error bar, the water abundance changes by 7 orders of magnitude. Exactly like I told you, right? So it doesn't matter how precise your calculation is. If you don't take this degeneracy into account, this is what's happening. A tiny change here is making a massive change here. And this is even worse than that, because the real degeneracy is between the water abundance and the pressure. So you're not backing out the water abundance, you're backing out the product of the water abundance and the pressure. So if you pick a different number for this, then this curve shifts up or down as well. So I presented to you a problem. It's not good enough to tell you it's a problem. I need to tell you solutions to the problem. So here are possible solutions to this degeneracy. The first solution is to break this is where the sensitivity to pressure becomes important. Because if I could somehow break the degeneracy due to pressure, I could say definitively that I have measured this radius, I know exactly what the pressure is. I can use hydrostatic equilibrium to scale this to the reference pressure and the reference radius, and I break all of the degeneracies. So one way of doing this is to use something called pressure broadening. So in atmospheres, collisions between molecules introduce fat line wings to the spectral lines, and this is a sensitive function of pressure. The problem with that is that this doesn't work at low temperature. So any temperature that's above 1,000 is not sensitive to pressure broadening. We have tested that. And the other caveat about pressure broadening, which I'm more troubled by, is that it's not understood. In fact, the prescriptions of pressure broadening in the community are, to say the least, ad hoc. And we can talk about this if you want after the talk, or you can ask me during the question. The second possible solution is to use the emission spectrum, because the emission spectrum probes directly photons, and it's sensitive to the temperature variation, and it's sensitive to pressure. But there's no reason that these planets, which are 3D beasts, would have the same local conditions on the day side as they do in the Terminator. There's just no reason to assume that. I'll give you some reason to assume that later in the talk, but in general, there's no reason to assume that. The third solution is the same as the first, which is that if you could measure the Rayleigh scattering slope in the optical, then you could measure exactly a certain radius, and you know exactly what the pressure is. The problem with that is, as I will tell you in the next problem, is that this only works when you have no clouds or aerosols. It turns out that a large fraction of exoplanet atmospheres are cloudy. So this method is not very reliable. The fourth solution, which we suggested in the paper, is that you could use an analytical relationship between the two to break the degeneracy. The problem with this relationship is that it's only accurate at order of magnitude level, but since your water abundance is varying over 7 orders of magnitude, I would say 1 order of magnitude is not bad. So that's the first problem. I would say the problem is not fully resolved, but it is a problem. And in fact, when the paper first, let me say a few more words about this. When this paper first came out, I got some angry emotional emails from people I will not name in this recorded talk. But then I gave the talk and I thought maybe I screwed up, maybe I made a mistake. But then I sent it to Mark Marley and he said, this is real, this is great. And then I gave a talk at MIT in front of Sarah Seeger's group and one of her students raised his hand and said, I've been struggling with that for 2 weeks. Then later, where was this? Niku Madhusuhan was visiting from Cambridge last week, and he said that just before he saw the paper come out, his student was struggling with the same degeneracy for also 1 or 2 weeks. And so now I'm convinced that this is real. So the second related problem is cloudiness. And it sounds very boring, it sounds very niche and specific. So let me motivate you with this slide. So this is, again, the width C3. I keep using the same wavelength. This is the transit depth. And here are 2 atmospheres. One atmosphere is a little bit hot, is hot, slightly cloudy, and has 0.1% water. The other is a little bit cooler, 500 degrees cooler, a little bit cloudier, and has 100 times more water. So 10% water. Can you tell which is which? The point is you can't tell. And that's the point. The point is that if you don't get a handle on the clouds, forget about answering the question of how much water there is. You can answer it in a forward calculation sense because you know everything that goes into your calculation. So you can put in how much water you want in your calculation, calculate forward, and voila, here's the spectra. But the inverse problem is much more difficult because the inverse problem is highly degenerate. And this is the crux of the problem, that you can't tell how much water there is, even if they are varied by a factor of 100. I did this on 2 minutes on my laptop. I'm sure if I tried really hard, I could find a solution where it's a factor of 1,000 or 10,000. I'm sure I could shift things around, I could give you 2 spectra that look the same. No, this is because the clouds mute the features. So the strength of the spectral features are muted by the clouds, but you can increase the abundance to counteract the muting. This is very naive. It's very simple. Now, related, so the obvious question is, how do you handle this? And now let me talk about something related. So you probably have seen this iconic figure many, many times in talks, probably even proposals that you have reviewed. And this Nature paper by David Singh, where he spends 150 HST orbits to get transmission spectra of about 10 objects. They're all the sizes of Jupiter and Saturn. So what your eyes pick out, because the models lead your eyes to pick out what they want you to pick out, is that there are slopes in the visible of different gradients, right? So there's a story in the literature, there's a narrative in the literature that says that all slopes in the visible are Rayleigh slopes. You see this a lot. You see the papers saying these are Rayleigh slopes. And the other narrative you see in the literature or in proposals, which I've had the pleasure of reviewing, are that the Rayleigh slope gives you the mean molecular weight and metallicity. Seems like magic. It gives you a lot. The reality is that the Rayleigh slope is only a Rayleigh slope if you can prove that the slope is associated with molecules or small cloud particles. And it's even worse than that. When it's molecules or small cloud particles, you can't tell which is which. There's no way from looking at the slope, I bet you my house, that you can distinguish between the 2 scenarios just with the slope. The second reality is that the slope, just because you see a slope, doesn't mean it's Rayleigh. Meaning it could be due to large particles and not small particles. And I'll show you this in the next slide. You do not get the metallicity. The metallicity is is the elemental abundance of oxygen and carbon and nitrogen and so on. So it's O to H, C to H, N to H. So the consequence is that the slope is not a good discriminant of whether an atmosphere is cloudy or not. You can look at it and you can look by feeling whether this is cloudy or not, but there's no way you can quantify it. So there must be a better way. Now let me talk a little bit about the slope. So I have no time to tell you where this expression comes from. All I can tell you is that this expression is used a lot in the literature and has been in the literature since 2008. So here's an expression for the pressure scale height as a function of the spectral slope in the observations in these units and an index called alpha. So alpha is -4 if it's Rayleigh scattering, small particles, and it decreases as the particles get larger. So the only observable in this equation is the slope. So really all you're measuring, you're not measuring H. You're not even measuring alpha. You're measuring alpha H. So that's all you're measuring. This is the reason why just because you see a slope doesn't mean that it's Rayleigh, because you don't know that alpha is -4. There are many variations on the theme on this equation in the literature. So in the original 2008 paper, this expression, which is kT over mg, was rearranged to give the temperature in terms of the mean molecular weight, the gravity, and the slope. You can trivially rearrange this to give m in terms of the rest, and this is Benneker and Seeger 2012. You can also rearrange this such that it's in terms of the surface gravity, and the surface gravity contains the mass, and therefore you claim that in a cloud-free atmosphere you can derive the planetary mass, and that's DeWitt and Seeger. So all of these studies can be unified by this one expression. So there's a better way of quantifying cloudiness. Again, before I explain this slide, bear in mind that I'm going for accuracy and not precision. So this is physically motivated, it's physically accurate, it may not be precise because of the assumptions that I'm taking. So the basic idea is that in cloud-free atmospheres, the difference in transit depth between the peak of a sodium line and the wing can be simply and exactly calculated with a few assumptions that if you're willing to accept them. And this is the expression. So this is the difference in transit radius between the peak and the wing of the sodium or potassium line, which is some complicated number multiplied by the scale height. And this complicated number involves things like the gravity, the scale height, the Lorentz profile, and so on. The reason why you can do this is because if you go back to Astrophysics 101, the void profile can be split into a Doppler core and a Lorentz wing only if the damping, so-called damping parameter is very small. In this case, the sodium line typically has a damping parameter that's well below 1, so therefore you can do this splitting with the caveat that you don't go too far out into the line that non-Lorentzian corrections start to be important. The other caveat is that you're assuming it's isothermal, which may not be the case. You're assuming that it's hydrostatic, it also may not be the case. And you're assuming that it's LTE, which may not be the case. I'll give you one scenario that this may fail, right? So it may happen that you are probing a pressure that's so tenuous that hydrostatic equilibrium is suspect, that UV radiation is important, all of the levels are not in LTE and so on. So you can certainly make that objection, but then once you make that objection, you have a system with 20 parameters, and you have no way to proceed. So this is the first, this I would say is the first wash at getting an answer and trying to refine it as we go along. So then the idea is quite simple. If you can calculate delta R, and you can measure it, and if they are exactly equal, then it's cloud-free. If it's any type of cloudiness would decrease the distance between the core and the wing. And the reason, the physical reasoning behind this is that sodium is a resonant line. It's a very strong line. So when you have cloudiness, the peak is not so affected by the cloudiness, but the wings are very sensitive to the cloudiness. And this is the reason why cloudiness would affect the distance between the peak and the wing quite strongly. So there's one wrinkle in all of this. To do this calculation, I need to know what the pressure scale height is, but I don't know what the temperature is. I can make the naive assumption that the temperature is the equilibrium temperature, but you can easily raise the objection that why should the atmospheric temperature be the equilibrium temperature? Look at the solar system, right? The equilibrium temperature of Earth is below freezing, which is clearly not true. The equilibrium temperature of Venus is the same as Earth, and that is really not true, right? So how good is this assumption, right? So there's one way to test it. You apply this index to the data, and if you get a number that's fairly close to 1, like between 1 and 3, then you can use this formula. Remember this formula? With the spectral slope with alpha minus 4 to calculate what the H is. You can compare this H to the equilibrium H, and you can calculate what the error is. So I could only do this for 3 objects, and I find that the error is about 17%. It's not bad. I was expecting 200%. So it's not bad. So now if you factor this error into error bars, you get an answer that's sensible. And this is the answer. So first of all, I take no blame for the size of the error bars. My motivation was to take the existing HST large program with all of its stated error bars and process this into this cloudiness index. So this is the cloudiness index. These are the objects in David Singh's sample. And this is the equilibrium temperature. And the only thing you can say is that tentatively, this seems to be inconsistent with a straight line. Of course, the error bars here are enormous, so the slope is mostly decided by these 3 points. So when this first came out, some people said this is plausible, so hotter atmospheres are less cloudy, sure. But given the size of the error bars, I was not too comfortable being too firm about it. But then a few weeks later, I was contacted by some people who wanted to write an ESO proposal. And they had data points using the FORCE2 instrument from the ground. And apparently, they do much better. So there are these 2 additional data points. And this one really gives me confidence that this slope is real. But at the end of the day, I don't really have any skin in the game about whether this correlation is real. I would like to know what the answer is, because thus far, when we try to look for correlations in the data of atmospheres, we don't really see any. So it's nice to see something that we can finally study. So this is, I would say, the first step towards quantifying cloudiness, and there's a lot more to be done. Now let me move on to the third problem. So the third problem is one of 1D versus 3D models. So there's a part of the community and the literature where people use 3D fluid dynamical solvers on a sphere that were designed to simulate the climate of Earth and adapt them to study exoplanets. So I started my career doing this. And so this is a run that I did in 2011. This is a run by Christian Manu and Emily Rauscher. This is the Ian Dobbs-Dixon. This is the Met office in the UK, and so on. This is analytical. And so the simulations disagree on many details. But what they do agree on is that the global shape of these tidally locked hot Jupiters have this chevron feature that's consistent with the infrared phase curves that are being measured. And you see instantly that it's not 1D. These are not 1D objects. And here's another simulation that's post-process, which is asking the question, do you get chemical homogeneity across different hemispheres? And the answer is no. It seems like the night side is full of methane and the day side is full of CO. So the upshot of this slide is that these tidally locked hot atmospheres are not 1D entities. They're 3D entities, and yet we routinely interpret them with 1D models. So we should be concerned. So in my group, one of the things we spent the last 4 years building, so we started thinking about it in 2011, started it in 2012, and finally published it in 2016, is we realized that the traditional GCMs are designed for Earth, like I told you. They solve a set of equations called the primitive equations. And it turns out these are the wrong set of equations. Because this set of equations, they assume hydrostatic equilibrium, they assume a shallow atmosphere, and they throw away certain Coriolis terms. So they're not general enough to say even do Jupiter. They're not general enough to do Venus, for example. And so we started thinking, could we do better? And it turns out that the meteorologists were already 5 steps ahead of us. So we dug deep into the meteorology literature. I spent 3 months reading just journal of monthly review of weather studies and things like that. And so after digging for 3 months, I found out that there's a climate center in Japan that came up with this scheme called the HEVI scheme, the horizontally explicit, vertically implicit scheme. And this scheme solves the fully non-hydrostatic Euler equations. And if you are interested in fluid dynamics and you want to learn more about this scheme, I'm very enthusiastic to talk to you about it because it's a wonderful scheme. It has many virtues. So that was one problem. The second problem was it turns out that fluid dynamics on the sphere is really, really difficult. Because on a sphere, in a regular latitude-longitude grid, there are two singularities at the poles, and your CFL condition goes to 0. So your time step goes to 0, and you can't proceed. So we spent 1 year just thinking about different grids. And we severely underestimated the amount of time. We thought it would take 1 month or 1 week. Turns out there's a whole literature just on grids. And the short answer is that there's no one magic grid that solves all your problems. It depends on what you want. So we tested 5 different grids. Most grids work if you care about integrating 10,000 time steps. That's easy. That's child's play. But in climate problems, you want to integrate 10 million or 100 million time steps. And over 100 million time steps, even tiny mistakes in the grid are not good enough. They explode into big numerical errors. So in the end, what we found out is that this grid is the most robust. You put triangles in triangles. This was discovered by the ancient Greeks 2,000 years ago, one of the Platonic solids, so I claim no credit for this. And the nice property of this grid is that the centers of triangles are the tips of pentagons. So you can put quantities either at the edge or at the center, and you can construct fluxes and la-di-da. And now the difficulty is that, as those of you who have played football before know, football is round, and pentagons are not. So you have to take the pentagons and the hexagons on the football and project them to the spherical surface. When you do that, you introduce a slight non-homogeneity to the grid. And if you don't correct for this non-homogeneity, it introduces numerical storms. And that problem took 3 months to solve. So after we solved that problem, we ran the standard test. It passed, luckily it's passed the standard test. So this is the standard Earth test. We could produce everything about Earth. These are the 2 jet streams. We could produce a hot Jupiter. And currently we are doing Venus. The postdoc who did this did his whole PhD on Venus and climate models. So he's doing Venus now, and we're thinking about doing Jupiter. That's another talk. So in my group, this is the long-term project that I started in getting funding in 2012. So this has about $1 million in funding so far. So we have a 10-year horizon. We have 3 postdoc and 4 PhD students working full-time on this problem. And roughly speaking, there are 3 nodes. So there's dynamics, there's radiation, and there's chemistry. And I have people assigned to each, and we think about the problems, and we try to really understand the microphysics. And the whole gist of this is that you're not trying to put everything into the simulation. You're trying to understand each and every piece, and then you're trying to understand what's the trade-off between computational efficiency and physical accuracy. That's the game. You can't put everything into the simulation. So we just published a GCM, which I gave you a flavor of. We have a chemical kinetics code I'm happy to talk to you about. This is more akin to high temperature combustion chemistry. And we spent a lot of time, almost too much time, thinking about radiative transfer and opacities. So let me show you one example of the coupling. So I want to show you this coupling, the coupling between dynamics and, by the way, we are very democratic in our mythologies. So this is the Greek god of the sun. This is the Roman god of alchemy, and this is the Norse god of thunder. So this is one example of the coupling. So if this is a slice at a certain pressure of 2 different molecules, and this is longitude and latitude. And if you made the naive assumption that it's in chemical equilibrium, this is like a Warp's 43b light planet, so like HD 189, 1300 Kelvin. So if you make the naive assumption that it's in chemical equilibrium, you end up with the answer that this really doesn't look 1D at all. You can argue that this molecule, CO, looks roughly 1D, that's fine, but this doesn't look 1D at all. Now if you do the full coupling with the dynamics, what happens is that the dynamics acts to wash out these inhomogeneities, and even more for CO. So the nice answer is that it turns out that for some objects, even though they are 3D, 1D is not too bad. These results are preliminary, by the way. It's a WARPS 43b-like planet, as I said. So now let me move on to the last two problems, which will take much faster because they are much more speculative, but I've come to appreciate that they are important. So the fourth problem is that of geochemical cycles, and we have a real geologist sitting in the audience, Eric Gaidos, who I talked to about these issues. So when I first heard about this, I thought the geochemical cycle, I fell asleep at geo, right? This is really boring. Then I started learning more about it and I realized this is really important because in the so-called long-term carbon cycle on Earth, this is the cycle that regulates CO2 over a 100,000-year timescale. What happens is that CO2 from the atmosphere reacts with silicate rocks on the land. This reaction is exponentially sensitive to temperature and moisture. The reaction produces eventually carbonates. And there are different types of carbonates. There's iron carbonate, there's magnesium carbonate, and calcium carbonate. And when I started reading the literature, I was confused why people were obsessed about calcium carbonate. I could never imagine why the other two carbonates were unimportant. Turns out that at the pH levels of the Earth's ocean and the temperatures of the Earth's oceans, iron carbonate and magnesium carbonate are very soluble in seawater, but calcium carbonate is not. So calcium carbonate sinks to the bottom of the ocean, gets subducted through plate tectonics, gets reprocessed, and then outgassed as CO2. And this is the reason why, when you read papers about people claiming that plate tectonics are important to make a planet habitable, it's because some people believe that if you break this cycle, then the carbon cycle will be broken. So this cycle of recycling CO2 takes roughly 100,000 years. And it's a thermostat. It sounds like a nice idea, right? So imagine if I had too much CO2 and too much warming in the atmosphere. Suddenly I had a Venus-like atmosphere. The whole thing is really, really warm. So the weathering suddenly increases exponentially because the moisture and the temperature goes up, and it draws down the CO2 till something manageable. Now, in the other limit, imagine that I had frigid temperatures, really cold, no CO2, so the weathering shuts off, but the outgassing keeps going, and it outgasses till the CO2 accumulates in the atmosphere and breaks it out of this frozen state. Sounds like a nice story, right? And now the question is, does this story has any proof? And amazingly, it does. So this scenario I just described to you is called snowball Earth. So when Earth was trapped in a snowball state. Sounds like a fantasy, but if you talk to geologists like Eric, and I have geologists, colleagues at Bern I talk to about this, you will find that rocks in places like Namibia have an astonishing structure where these rocks are traces of glaciers, so really cold ice ages in the Earth's history. And these rocks called cap carbonates are traces of rapid weathering. And the reason why this is astonishing is that if I remember correctly, the time axis in this gap is on the order of decades or centuries, which is nothing compared to that, right? So there's evidence in the Earth's history at some point that we were in a frozen state and broken quickly out. And this is evidence that this cycle is not just a theoretician's fantasy. Now, why is this cycle important? This cycle is important because when you want to talk about habitability and you want to talk about Earth-like planets, it has basically nothing to do with planet formation. The atmosphere of Earth looks nothing like the atmosphere of the sun. And if you take the approach that you would like to calculate the Earth's atmosphere from first principles, starting from the molecular cloud to the star and the solar system, I'll challenge you to do that. My prediction is that you will drown in free parameters, maybe 500 of them. Instead, the Earth and habitable planets are controlled, their atmospheres are controlled by geochemical cycles. And the simplest way to understand the habitable zone, which is the range of distances from the star where you have liquid water on the surface of the planet, is to understand an atmosphere with 3 components. And once you understand this simple model, you understand everything on the diagram. So you need 3 components. You need a incondensable greenhouse gas, CO2 for the Earth. You need a condensable greenhouse gas, water. And you need an inert gas, nitrogen. So the inner part, the inner boundary of the habitable zone, roughly speaking, with caveats, is when the condensable greenhouse gas becomes incondensable. So water becomes completely gaseous and doesn't go back. The outer boundary is when the incondensable greenhouse gas becomes condensable. So CO2 freezes out. And the inert gas does subtle things that are not fun or easy to explain in 1 minute. But now, once you understand this, you can play games with this, right? So what if I remove just enough water from the atmosphere that you never get into this runaway greenhouse? You get this dry desert worlds. Then you can push the inner boundary a little bit to the left. And this is what Andreas Zomm and Sarah Seeger have come up with. Now, if you play a different game, which Ray Pierre-Humbert and Eric Eidos have done, you take out the nitrogen as the inert gas, and you insert molecular hydrogen, which has a much lower condensation temperature, and has a very peculiar effect called collision-induced absorption. Then it turns out that because of these 2 properties, you can push the outer zone much further out, a factor of several. So the message in this, there are 2 messages. One is you should worry about how your greenhouse gases are regulated, so the geochemical cycles. And the second message is that the habitable zone depends entirely on what you assume for the atmosphere. So it's meaningless to take a standard habitable zone and overlay it on observations. It doesn't make any sense. Now, let's talk about related issues. So there are 2 related things to talk about. One is the faint young sun, and one is early Mars. So the executive summary is that astronomy tells us that the sun was fainter in the past, and yet geology tells us that the early Earth was warm and wet. So how do you reconcile this? How does the Earth know when to warm itself and switch itself off? And if you talk to people like Eric, the carbon cycle is a natural solution to what we astrophysicists call a fine-tuning problem. So this is a natural solution. A related problem is early Mars. Again, geomorphology on Mars, you look at all these features and you try to reason that they are due to water, and there's a whole literature and a whole community doing that, who have managed to convince themselves that early Mars indeed had water on the surface. And now the questions you should ask is, how did the atmosphere of Mars evolve? And what was its chemical composition at different epochs? And yet another question is, was the carbon cycle ever important? And there are suggestions on how to reconcile theory and observations, but again, this belongs to the broad category of geochemical cycles. So I leave you with a bunch of open questions for this 4th problem. So you can ask questions like, is water the only solvent? Are the rocks made from the same minerals? How does the cycle behave in different atmospheres? And how does the cycle behave when you change the acidity of the solvent, in this case water? Are there regimes of parameter space where the carbon cycle breaks? And what are the consequences? All of these questions are either unanswered or partially answered. And currently what I'm thinking about. So in the last few slides, let me talk about biosignatures. I will jump straight to talking about Sarah Seeger's approach because I think her approach is the most novel in the field. Many of the approaches about biosignatures have been variations on a theme of Earth, very Earth-centric and a small departure from Earth. Sarah's approach is radical, to say the least, which is she takes all of the molecules in existence, passes them through a filter, and then comes up with different classes of biosignature gases. And the main message to take away is that one of the challenges to tell if something is a biosignature is to tell it apart from geology. It turns out that the same gases that life uses in metabolism, say like methane, rocks are also very talented at making methane. So just because you detect methane doesn't mean it's a biosignature. So this would belong to a type 1 biosignature, as Sarah calls it, because this has a geological false positive. There's a type 2 biosignature which comes from biomass building, but in these papers they didn't find any that were present in enough quantities to make it to the list. So currently there are no known type 2 biosignature gases. Type 3 biosignature gases are due to physiology. So not due to what you eat, but due to what you use to perform functions like stress and signaling and so on. And these are claimed to have no geological counterparts. So to say more about this approach, so it's a brute force approach, right? You take all of the different CHONOPS molecules, you make all of the different combinations you can in the computer, or 13,000 of them. You check this against different databases, and you check this against the literature on molecules used by life. It's a brute force approach. So you come out with a list like, these are the molecules made by life, and these are the molecules not made by life. And then after you do this, you then ask the next question, which is, which of these molecules are stable in a specific type of atmosphere? That's again very important, because whether something is we tend to have a static idea of biosignatures. Here's a molecule, it's a biosignature. It turns out that these biosignatures are very dynamic. It depends on the type of the atmosphere, it depends on the UV environment. Let me give you one surprising example. So you will never think of ammonia as a biosignature, right? You will never think of ammonia. But in a special circumstance, which is in an ultraviolet radiation-rich environment, any primordial ammonia would be readily destroyed by photolysis. Now, the only way to maintain ammonia in such a hypothetical situation is for life to exploit the energy gradient given by this reaction called the Haber process. This is the industrial process used to make ammonia. And if there's one thing we have learned about extremophiles on Earth, is that every time you give them an environment with an energy gradient, they exploit it. So another way of saying this is that it's much harder to solve the problem of what's the definition of life. It's much easier to solve the problem of what does life need. And what life needs, we probably don't object, is that it needs some kind of energy gradient. And these are, I don't really have time, so let's skip that. Now I would like to leave you with some one-sentence summaries of what I talked about. So I would say that the study of exoplanet atmospheres has come of age. Transmission spectra lack an absolute normalization. Hotter atmospheres may be less cloudy. Again, I'm not invested in this result. Let's just see what the answer is. Dynamical radiative chemical couplings are key and very difficult to do. Geochemical cycles control the composition of secondary atmospheres like Earth, and biosignatures depend on the atmospheric properties. So in 2 more slides, let me show you this. So there are 2 books on exoplanet atmospheres. The first one is by Sarah Seeger. In fact, it's the inspiration for writing the second one. So I went to her a few years ago, and Sarah is one of my mentors. So I went to her a few years ago, and I said, what do you think of me writing the follow-up to your book? And she's very frank, and so if it was a stupid idea, she would give me 10 reasons why. In fact, she was very encouraging, and so I chose the same publisher, which is Princeton, and the same editor, which is Ingrid. And it took me 2 years to write the book, and here's a copy for the first student who shows me the student ID. And I would like to walk you a little bit through the contents of the book before we end. So the point of the book is not to teach you everything about everything. No book teaches you that. The point of the book is to teach you a little bit about everything. Because when I started picking up this topic, I had no PhD advisor. I was doing it completely in the dark. And I was reading textbooks from geophysics, from atmospheric science, from stellar physics. I was reading like 20 textbooks and lots of papers. And my thought was, no student should have to go through this torturous path. So I thought it would be useful to put it all in one volume, roughly 300 pages. And you will see that it goes for breadth rather than depth. And the trick behind that is to relegate all the boring standard stuff to the problem sets. And so there's a theorist review of the observations. There's a introduction to radiative transfer, because I've taken many courses of radiative transfer as a student, and there are two ways to teach it. One is you teach it like a mathematician, and you walk out of the class after 6 months knowing nothing about radiative transfer. So this chapter teaches you what tau equals to 1 is, if you understand that. And then there's a chapter on two-stream radiative transfer. There's a chapter on how to use atmospheric opacities and calculate them. There are 2 chapters on chemistry, which surprisingly you can go very far on paper without using a computer. There are several chapters on fluid dynamics. And one of my most beloved chapters is on the de Laval nozzle. I can tell you why as well, and so on. And there are different appendices for things that you should not have to check 5 books to find out. And there are Python scripts to generate figures. So essentially it's self-contained, and you can use it as the first book to launch yourself into this research field if you wish. And thanks for putting up with my overtime. And I'll be happy to take questions.
Now it works. Okay, many thanks, Kevin, for this wonderful talk and overview of the current open problems in extrasolar planetary atmospheres. There must be many questions. Please go ahead. Yes, Caitlin.
So I had a quick question on your cloudiness parameter. So I think you said
it's a posteriori check. So meaning that you assume something to be true, you go ahead with the calculation, and then you check after the fact that it's consistent with what you started with, basically.
But you can't infer to what extent those other assumptions are saying anything about the error.
Right, but then the problem is that it's better than the alternative of having 0 bounds on your error, I would say.
So next question by Roy. Please shout, this thing is not working.
I will. We spent quite a bit of time talking about transit spectroscopy and talking about all the problems and degeneracies. We didn't talk so much about daytime eclipse spectroscopy. Now very soon we're going to launch an observatory that will be great, James Webb. Observing time will be extremely costly. What should we do?
So that's a great question, and in fact, in Bern we have this active discussion with Brice Olivier Demery, another professor at the CSH, as you know, and one of the questions we're asking is, should we go for emission or transmission? And most people, the reason why I presented this is that most people make the argument that transmission is cheaper and easier, and the reason is because the wavelength at which you probe transmission spectra depends only on the blackbody peak of the star and not on the temperature of the planet. Whereas for emission spectra, you are going with the sigma T to the 4 of the planet, right? So as the temperature of your planet drops, your wavelength shifts drastically to longer wavelengths. So that's the standard argument that people give for saying that we should go for transmission and not emission. And part of presenting this to you was to push back on that standard picture. But I don't have the answer for you, and I also don't feel comfortable saying it because it's part of our Bernese strategy for GWST.
Glenn.
Maybe a very naive question, but so you showed this chemistry between the Arnold and the Greenland radius normalization and pressure for one capacity, and then showing that it's very small depending on the two normalization. These two normalizations are the same for different capacity measurements?
You mean the R0, how to fix it? In terms of the theory, it's completely up to you. So R0 is a wavelength-dependent quantity. You can choose any wavelength you want. But then the challenge is after you choose the wavelength, you should figure out what the pressure is.
But if I somehow fix them or couple them and I measure different capacities and I have a reason to physically motivate what the ratio between different capacities, can I start breaking that geometry then?
That's very insightful, and the answer is that if you have n molecules, you would get the n-1 ratio of abundances very precise, and you would not get the normalization precise.
But is that already useful? The relevant capacity?
It depends on the question you're asking, right? So if my question is, do I see CO, water, and CH4, and the answer is yes, no, yes, then that's my answer. But if my question is, I would like to know water to within 10% so that I can decide if there's life on this planet, then yeah, you're in trouble.
I have a question regarding the first part where you talked very longly about the spectra problem, which I think is pretty brilliant, really big part of that. And you have this one very nice information about three parameters that are connected right. It's the capacity, the surface gravity, and the pressure. But I thought that they actually have time.
Go on, I'm listening.
Have the pressure stay with it. It's technically wrong.
That's actually gravity related.
Then the temperature and the molecular weight.
The temperature is part of the fit, and the gravity is something that you can measure.
Yeah, but the mean molecular weight is all.
The mean molecular weight is something that, in the case of hydrogen-dominated atmospheres, you can safely assume. But I agree that in the case of secondary atmospheres, then you're in trouble.
Exactly. So only working to capture the surface gravity and running out of temperature. Okay, that's it.
Right, and the statement here is that even if you knew all these quantities, you're still in trouble.
So, you had a question?
Yeah, it's a little bit towards the end of the philosophical part. So, we have the question of which position, how far are we in your opinion to evaluate these possibilities? What gradients are possible under all kind of radiation or pressure coefficients and so on. I mean, is this something we still have to do, or is it known to a large degree? Because we have this diagram where all the three elements there.
Right. So I personally don't do any of this work yet, but I'm an enthusiastic reader of Sarah's papers, so you can read them. And in these papers, she lays out various scenarios for how the atmospheric environment changes the nature of the biosignature. It's not an answer I can give you in 30 seconds. But for example, a canonical biosignature is methyl chloride. The slide I skipped, so it's this one, CH3Cl. This, for many years in the habitability community, has been one of the standard biosignatures. Turns out that this is not true for certain atmospheric configurations. So whether the atmosphere is oxidizing or reducing plays a strong role in whether this is stable.
Well, let's go to the far right.
So we have, I guess, another problem on stellar activity.
Say again, sorry.
Stellar activity, for example.
Absolutely.
Yeah, so but since you didn't talk about it, do you have any comment on that? Like in stellar spots that we need some kind of like gradient scattering feature like
I didn't talk about it not because I'm not aware, but because from the standpoint of a theoretician, it's a contaminant and not a theoretical problem. Is my answer to you. But we do think about it, and we are investigating, for example, the dependence of the indices on, say, the activity. And so there are certain predictions if, for example, For example, if the cloudiness index trend is due to stellar activity, you can pose that question. It's a very fair question. Then it will predict a certain trend. And when we look at the data, we see something that is not quite that trend and not quite not that trend, right? So it's ambiguous, right? Go ahead.
You talked a lot about illuminating planets. What do you see are the theoretical challenges for self-luminous objects in terms of modeling?
That's a great question. So for this object earlier, there are many challenges. So this object, these objects in general. So the irony is that the higher spectral resolution and the better spectral coverage actually doesn't save you. And the reason is because you don't know what the radius is and you don't know what the mass is. And so you're very precise in the spectral space, but very inaccurate in the radius mass space. And in fact, on average, when you take everything into account, transiting planets are better to interpret than directly imaged exoplanets. This to me was a supreme irony and very disappointing, to be honest with you.
Any questions here?
I was just curious. So you said you were planning to study Jupiter with your dynamics model. So wondering what you thought of the sort of recent Juno measurements suggesting that there's equatorial upwelling of some ammonia opacity from the far depths. Is that as big a surprise as it seems? Is that something you want to look at?
Honestly, I know nothing about that literature, so the honest answer is I don't know. We wanted to do it as a computational exercise to satisfy some of the computational urges in my group, of which I do not have.
So, Glenn?
So on your geochemical cycle, a little bit back to the bonus point. So water is a solvent. Doesn't matter how much water is there. So is it important that we measure, for example, that cycle that there is water, or does it actually matter how much water? I'm the same for the solid material. Is that important?
Your question has many questions in it. So the cycle, to zeroth order, the cycle is very sensitive to water. And most astrophysicists, they construct this spherical cow model in which the weathering rate is proportional to temperature, water, and exposed land area. Turns out that what limits this is not just the exposed land, but the fact that once you react with the exposed rock, there's a protective layer over it. And you are limited not by the amount of exposed land, by the amount of erosion that happens, and that's very difficult to model. The other complication is that imagine you have the water world. You have a world in which is completely ocean covered, and you have some kind of surface, but it's all underneath water. Then the astrophysicists will say, there's no weathering. Turns out there is. Turns out that there's a seafloor weathering where you are limited by the amount of CO2 dissolved in the seawater interacting with the exposed rock at the bottom of the ocean that is controlled by erosion and overturn, which are impossible to model. So again, these are all these complications. The good news in this story is that about the rock is that we are not totally in the dark. So if you look at, I talked about the sun, right? If you look at the sun and you look at the volatiles in the sun's photosphere, the tau equals to 1 surface in the optical, you will see that the sun's volatiles look nothing like the Earth's volatiles, but the sun's refractories, magnesium, silicon, iron, look a lot like the Earth's mantle, to within 10%. And in fact, the refractories of the sun's photosphere are mirrored in not just the mantle of Earth, but the mantle of Venus and the mantle of Mars. So to lowest order, the refractories in the stellar photospheres tell you a lot about the rocks on other planets. And in fact, when you look at stellar abundances, you will see that it's not like you can have any bloody star you want. It's more or less sun with some error bar. Right? Most stars have abundances that are very much like the sun, right? You don't have stars with C/O ratios of, say, 25. They're all clustered around the sun. So we have some handle on the rock, I would say.